So the second part of section 4.3 is conditional probability. So it's the probability of an event given that some other event has already occurred. So this line here indicates the word given. And the way we read this is that it is the probability that event B occurs given that event A has already occurred. Now, although you'll see something very exciting like this, we focus a little bit more on using tables for these problems, and I think you'll see how it works once we look at some examples. So let event A be that today is your birthday. If it is, happy birthday. And event B is that your birthday is in this month. So are events A and B dependent? That means is the probability that your birthday is in this month, is it affected by the fact that that we already know that today is your birthday? And from that, we would say yes. Because if you're asking the probability that your birthday is in this month, but it's given that today is your birthday, well, then we know that your birthday is in this month because it's today. So the probability that today is your birthday, you might say, well, that's 0 because today's not my birthday. But if we were to just randomly choose somebody, the idea here would be that one day is your birthday out of the year and there's 365 days out of the year. So we're kind of ignoring leap year in this case. Sorry if your birthday is on the 29th of February. So 1 out of 365 is about 0.0, I just got a little bit tight with my zeros there, but 0.00274. So it's pretty small, the probability that your birthday is today. Now this is saying, what is the probability that today is your birthday given that your birthday is in this month? That's how this is read. Probability that today is your birthday given, don't forget, given that your birthday is in this month. So if you already know that your birthday is in this month, then what is the probability that today is your birthday? Now, it really depends just a little bit on what month we're talking about. I'm making this video in August, so August has 31 days. So the probability that today is your birthday, given that your birthday is in this month, would be 1 out of 31, which is, because one day would be your birthday, 31 days in the month, 0.0323. Okay, now the other one is read, for D, it's read like this. The probability that your birthday is in this month, given that today is your birthday. That's how that's read. So we're reading B first, of whatever event B is, given that event A is a given. We already know that it has happened. So the probability that your birthday is in this month, given that today is your birthday, well, we know that today is your birthday, so what's the probability that your birthday is in this month? Well, that's certain. And the probability of an event that is certain is 1. So there's a 100% chance that your birthday is in this month if today is your birthday. Okay. And let's look at a couple tables. So we're talking about Passengers of the Titanic. This is not just a movie starring Leonardo DiCaprio. It's an actual event that occurred in the world. So what you can do if you want is pause and sum all the values in the table. They're not as nice and pretty as some of our other ones. Notice that there's 2 pieces of information that we know about everyone in the table. My numbers don't look as nice as I'd like to see here because of the way the light is shining. Okay. So for every person that was on the Titanic, there's 2 pieces of information. Was it a man, a woman, or a child? And did they survive or did they die? So again, a lot of statistics are rather morbid. So let's look at some probabilities here. The probability that if we were to put 2,223 people in a bag and pull one out, randomly selected, what's the probability that we would be pulling out a passenger who died given that the person was a man? So notice my notation there. So we're given that the person was a man. We already know that the person was a man. So it's almost like now we're just taking the men and putting them over in their own separate bag. We're given that it was a man. So we're not even talking about the women and the children now. We know that it was a man. So that becomes our new denominator. So notice that the sample size is being reduced when we have that given. The probability that we get a passenger who died, now we're thinking, okay, how many men died? Because it's really saying, what's the probability that a man died? And since there were 692 men and 1,360 of them died, that means that about 0.804, so about 80% of the men that were on the Titanic died. And you might know why that is if you're familiar with the history, but women and children were given the life rafts first, and there were not enough life rafts for everyone. So if you want, see if you can pause and do B, and then come back and see if you got your answer right. You can even pause and try to do B and C, and then come back and see what you got right. So the probability that now we're back to our 2,223 first. We put them in, we're going to pull somebody out, but now we want to know what's the probability that we get a woman, but now we're given that the passenger survived. So again, that given information changes your sample space. We know that the passenger survived. Whoever is being pulled out survived. So now we're down to only these 706 people, only the ones that survived. And then what's the probability that it was a woman? We think of how many women survived. So you should never have a fraction that is more than one. The numerator should never be larger than the denominator. So if that ends up happening, something weird, you got to check it out. So if I want to use the formula on the last page, I'm going to call this event B, that's choosing a woman, and I'm going to call this event A, the event that a passenger survived. Then, again, this is using the formula from the last page, we'd have two fractions, and then we have to do this math and get the same answer, and it's a bit of work, and that's why I wanted to show you, but also get you to see that the way I'm talking about it is hopefully a little bit easier. So in the numerator, it's the probability of A and B. The probability that you get a woman that survived, and that is 318 out of 2,223. Now in the denominator, it's the probability of getting someone who survived. That's 706 out of 2,223. And then if you're familiar with fraction math, the answer to this, dividing by a fraction, is the same as multiplying by the reciprocal. This takes you way back. And then you simplify the 2,223 and you get the answer that we got already. So you can use this method, the formula, if you understand it. You can read more about it in the book, but it is one way to look at it. But the way I'm talking about it works as well. So the last one here, if you maybe paused, you can pause now if you didn't, to see if you can get the right answer. So we want survivor given that the passenger was a child. So again, now we're told that we're only talking about the children. What that does is reduce our sample space to saying we only we know that it was a child that we're talking about. And then we want in the numerator those children that survived. And there were 56 of those. So when we do that, we get a 0.514. So about 51% of children survived. And we'll do the last problem. So this is very similar. We've got some nice numbers here. You are welcome to pause, see if you can get any of these, see if you can work on the notation. That's really important. And then come back and see what you were able to do on your own to know how good of a shape you're in. So these examples kind of show you that you don't actually need to have the word given to still need to use the idea of conditional probability. So this says, what is the probability that a part-time student is female? So notice we're being given that we have a part-time student. And we want to know what's the probability that the part-time student is female. So we would write that like this. We know we have a part-time student, so that is 140. And we're asking how many are female, and that is 80. That's about 0.571. Then what is the probability that a randomly selected student is part-time given that they are male? So now we're back to using the word given. So probability of part-time given male. So once we know that we're only talking about the males, we're over here talking about only 80 students, because there's only 80 male students that were observed, the status. And part-time, we look at how many part-time males we had. So 60 out of 80, so that's about that's 0.75 exactly. And the last one, again, not using that note like the word given, but indicating given, because it's saying a randomly selected female. So not just a randomly selected college student, a randomly selected female. So we know that we are already talking about the females. They're over in their own little container. There are 120 females. We're talking about them. And then we want to know about full-time. So at that point, we would take a look and say there's 40 full-time females. And so that's about 0.333 to 3 significant figures. And that's conditional probability and the end of chapter 4.